define a calculus of this deductive system, and then we're gonna study it. So have this rule, which is called the identity rule. This was a rule that Gensen introduced, and if you think about this logically, it's saying that A entails A. Under the hypothesis A, the conclusion A holds. Okay, so it's an axiom of logic. Now there's another rule, which is called the cut rule. Now, I'm writing Greek letters to stand for lists of formulas. So this list of formula, I'm also sometimes going to call it a context and use Greek letters gamma, theta, delta to range over these contexts. So this rule is called the cut rule. If we think about this in terms of logic, it says that if you can show A under hypothesis theta, and well, with some additional hypothesis gamma together with A and delta, you can show B, then you can show B from the hypotheses gamma, theta, and delta. This is kind of expressing the idea of using a lemma in order to, we prove B by using a lemma. We use A as a lemma. So this is what Gensen called the cut rule. Now, these are kind of generic structural rules. Now we have two rules for dealing with the product. And yet we're going to think of the A times B as a kind of conjunction, A and B, but it's going to be a very restricted form of conjunction. So what are the rules? There's two rules. So, just writing it down, this is called the left rule for the product. And what it does, if you read it going from the bottom to the top, it's taking a product and turning it into a comma. So we have a list of formulas here. We have A times B, and then we have a list delta, and we break up A times B into two formulas, A and B, at the left of the context. Then another rule, which is called the right rule. And it says this. If you think about this as conjunction, if we can show A under hypothesis gamma and B under hypothesis delta, then we can show A and B under hypothesis gamma together with delta. Now, these are all the rules. So these are the rules of the system that we're going to use. Now, let me just talk a little bit about the connection to the original sequence calculus. So Gensen had something that looked a lot like this, but he had some additional rules. So he had some additional rules. For example, he had a rule that looks like this, that so this gets to your question. So I'm allowed to freely reorder the hypotheses in the context. So it's the same to use B and A as using A and B. So he had this rule. He also had a rule that looked like this. Which says that if you read it from bottom to top, to prove this, I want to prove C with some hypotheses gamma, A, and delta, I can duplicate the hypothesis A. So I can reuse the hypothesis as much as I want, or alternatively, I can throw it away. So this was in Gensen. These were part of Gensen's original system. But we're not going to have these rules, okay? they hold under the classical interpretation of logic for conjunction because A and B is the same as B and A. And if you have A, then you have A and A. But it's not going to hold for what we're interested in. Now, let me say, this idea, in a way, goes back to Lambeck, Joachim Lambeck, in 1958. He wrote this paper called On the Mathematics of Sentence Structure, where he observed that if you take Gensen sequent calculus and if you get rid of these rules, then you get a system that, the product, the idea you can think of your context as a string, and you can think of building proofs as sort of doing building parsing derivations. So he had an application to linguistics. The idea was that if you get rid of these rules, then you get a logic which somehow lets you do some linguistics. Now the rules that he had were almost the rules that I wrote right here, except that he had a stronger rule, which is that you're allowed to do this whenever you have. So he had the possibility of having additional formulas here. So the idea is that whenever you have a product A times B to the left, you can turn it into a comma. That was Lambeck's original rule. So all that I'm doing is restricting his rule and saying that you can only do this when your formula is at the very left. So maybe this is all very abstract, and I'll give you an example now.
You don't have negation.
Right, so this is, calling this logic is a bit of a stretch. All we have is conjunction. In Gensen's original calculus, you had lots of different connectives. You had conjunction, disjunction, negation, universal existential quantifiers. In Lambeck's calculus, you had product and you also had implication. Here we just have product. So
you just have one. Sorry.
So just the product, which is just like a conjunction.
And the arrow.
And the arrow, but the arrow is like a meta arrow.
Oh.
It's so. Right, so we had an example of something which we can derive. So So this tree is below this tree in the rotation order, but now how can we derive it? Well, we have different ways of deriving it in this calculus, but let me show you one way. So this corresponds to the word A times BC times D, and this is A times B times CD. So let me derive now that A, B, C, D entails A, B, C, D. Okay, so we're going to try to prove this directly. This thing entails this thing. How can we do that? Well, we can use any of these four rules. We can use any of them that apply. So let's begin. We're going to begin by applying the left rule. So I'm going to write L for the left rule. We return this product, A, B, C times D. We turn it into a comma. So now this is going to become A times B, C, comma D, entails A, B, C, D. Okay. This might look a bit strange if you haven't seen this before. I assume no one has seen sequence calculus before, but just bear with me. So now we have this as our new goal. We want to show now that these two formulas entail this formula. So we're going to apply the left rule. We're going to turn this product, A times BC, into a comma. So now we have A, comma, BC, comma, D, A, B, C, D. And now, I should have shifted this over a little bit, but now we're going to, well, can we apply the left rule again? What can we do here? So now we want to show this thing. A, comma, B, C, comma, D entails this. We can't apply the left rule because A is not a product.
BC is a product.
BC is a product, indeed.
But it's not on the left.
But it's not at the very left, so we're not allowed to apply that rule. We could apply the cut rule, but let's try to do something else. So let's apply the right rule. And to apply the right rule, we have to split the left-hand side into a gamma into a delta. So we're going to split it into A entails A, and BC, comma D entails B times CD. Here, now this is just an axiom, so this is the identity rule. Now going here, now we're going to keep going, so now we have a product on the left. B times C is at the left, so we apply the left rule. We turn it into a comma. And now we're pretty good, so we apply the right rule. We have B entails B, axiom, C comma D entails C times D. Apply the right rule again, C entails C, D entails D. Okay, we're done. So we've shown that this word is below this word. Okay, now to give you a bit more intuition, I'll give you a non-example now. So we know that this tree is below this tree in the order, but we don't have the other way around. So this tree is not below this tree. But let's try to prove it anyways. Okay, so we can start the same way. We'll apply the left rule, and we turn the product into a comma. But now what do we do? So we'd like to apply the left rule, right? So we'd like to apply the left rule, but the problem is we can't because we have, this is not a product. Nor can we apply the right rule, right? To apply the right rule, we would have to split the left-hand side. So maybe, let's say we apply the right rule. We'd have to split this list into two pieces, one of which proves A times BC, and the other which proves D. So maybe, we could try to split this as A entails A times BC, and BCD entails D, but this is not going to work, because these have different sizes. So that's not going to work. Well, maybe we could apply the cut rule. And maybe, maybe we could apply the cut rule, we don't know. But it turns out that even if you apply the cut rule, it won't work. What would work is if we could apply Lambek's original rule, and we turn this product into a comma. And then we apply it again to turn this product into a comma. And now we can apply the right rule. And okay, so we have A comma B, C. We split this into this part, which A comma B comma C, which proves A times C and D which is D, and okay, we can keep going. But we had to apply Lambeck's versions, the left rule, which we don't have. So in fact, you can't prove this entailment and this entails this using this calculus. So that gives you a bit of intuition. Really, there's something about this restriction, the fact that we restrict this rule to only apply on the left side that introduces this asymmetry between the left and the right. Okay, so I have how much time? 4 minutes. Okay, so I think we're going to get to maybe amazing facts number 0. Okay, so I'll try to give you a sketch of how to use this. So I said that it turned, here when we were back at this stage, let me, okay, so there's three things that are going on. So the first thing that we want to prove is that, in fact, this really captures the Tamari order. So I'm going to just state that. So A is less than or equal to B, just in case A arrow B is derivable in the sequent calculus. Okay, and proving this is not so hard. The completeness direction is actually very easy. So the fact that you can derive any valid entailment using this calculus, that's pretty easy. The soundness direction, the fact that if you can derive A entails B, then in fact A is below B in the order, that's a little bit, just a little bit harder. And part of it is interpreting, what is the meaning when we have a sequent like this, a general sequent, if we can prove that some list of formulas entails B, what does that mean in terms of the order? We have to give an interpretation, and the interpretation is that you can think of this as a left-associated product. So that means, if this holds, then A0 times A1 times ... times AN. So the left-associated product is less than or equal to B in the order. So to prove this soundness direction, we have to generalize the hypothesis to give an interpretation of general sequence, and it's interpreted in terms of this left-associated product.
Now it's an ordered list.
It is an ordered list. Yes. Yeah. It's important that it's an ordered list. So again, you can only ever prove an entailment between two formulas if they have the same underlying frontier of leaves. But the original motivation for sequent calculus that Jensen originally had, it's not just that it's a very powerful system, but in fact that it lets you prove properties, very, very interesting properties. And one of the theorems that he proved, he called cut elimination. And what it says is that this rule, the cut rule, is in a sense redundant. And it might seem a bit counterintuitive at first if you think of the way that we make proofs. And I said that the cut rule is kind of like introducing a lemma. The cut rule, in a sense, says that you never need to introduce lemmas. If you prove something using a lemma, you can always get rid of the lemma. But in fact, you can.
In real life, you can just treat and put the lemma in the body of the proof.
Yes. But what if you use the lemma later?
Yeah.
Well, okay.
You can do it again.
Well, that's the idea. That's his proof. So that's basically this theorem that he proved in the 1930s. It was basically that. Now, we can do a similar thing here. We can do the same thing, so we can show that this rule is redundant. In fact, even we can restrict a little bit more. So in fact, this rule can be restricted to, I'll write P here. So P is a leaf. So we can restrict the identity rule to leaves. We don't need it for general trees. And also we can restrict this rule a little bit. I'm calling so that gamma is an irreducible context, where by irreducible I mean that it doesn't have a product on the left-hand side. So the idea is you can think of, well, if I have any sequence I want to prove, I have a strategy for trying to prove it. The strategy is, well, I look at the left-hand side. Is it a product? If it is, then I just try to apply this rule. And now, then from A times B as the leftmost formula, now I have A as the leftmost formula. And I look at A again, is it a product? And I apply this rule again. Keep going. Eventually, the left-hand side is going to be just a leaf. That's what I mean by irreducible. Now you can try to apply this rule, depending on if the right-hand side is a product, you try to apply this rule. And you keep going until eventually you get to these rules.
Now we'd like to answer questions in private, personally. Thanks for a beautiful talk. Everybody